use that to do the world's first faster than classical quantum computation. So here we're implementing Grover's search algorithm, and we're doing it just by programming the dynamics of nuclear spins in its spin resonance. And then went on to implement Shor's algorithm. This is one of the most significant quantum things you can do. You can break classical cryptography by finding prime factors efficiently. And so this was a landmark experiment that proved 15 is 3 times 5. But it did it in fewer steps than classical, and it was done by programming molecular spin dynamics. Now, quantum computing gets a lot of attention, but there actually aren't that many important problems. You can do searching, you can do factoring. The really useful thing you can do with a quantum computer is quantum mechanics is exponentially harder to simulate than classical mechanics, because you have to simulate all states of the system. So a quantum computer can emulate another quantum system, was a very important result, and you can do very efficient quantum simulation, and that turns out to be really useful. So, going back to all of this, I won't grade you on the final exam for how well you remember how to make a teleporter, but what does this have to do with your labs? So that was explaining quantum mechanics. Some of the current things in my lab are, we're making what are called adiabatic quantum flux parametrons, which are superconducting devices that are a double well potential, and instead of creating and destroying charge in a transistor, you move these quantum states around. And what's interesting is you can do that as zeptojoules, so milli, micro, nano, pico, femto, atto, zepto. Zepto is just above KT, thermodynamic limit, so very low energy. And you're going to hear in a little bit about a quantum Lego AR project. This is a project in my lab where literally the proposal was we wanted to make a quantum Lego. So with a colleague, Naray's group at MIT, we're making nanoclusters of tens of atoms, and then we're studying when bricks become bonds, the crossover between mechanical joints and quantum joints to study nanoassembly. So, what does that have to do with you now? When you go in a fab lab, almost every single thing you do is quantum. And one of the goals for today is to appreciate that and start unpacking it. So, you just heard from Xtool. We love their lasers. Laser is the favorite tool in the lab. Laser light is a fundamentally quantum state. So, there's a gain medium. It has discrete quantum states. You pump the ground state to an excited state. It decays to a lasing transition. And then there's what's called stimulated emission, where a photon coming in meets the atom in the excited state, and it stimulates the emission of another photon, and that photon is phase coherent. So it's actually creating a quantum state of light, and that's what lets you make this parallel focused beam. And so any time you make a keychain on a laser cutter, you're actually doing a quantum project, a quantum lesson, and I think it'd be great to be able to share what's going on in your laser. When you use a motor, you're using a magnet. Magnets are incredibly subtle quantum phenomena. So magnetism comes from the property of spin I'm talking about. Spin acts like the particle is a spinning magnet, even though nothing is spinning, but mathematically it has the same structure. But magnetism doesn't come from the magnets lining up. It actually comes from what's called an exchange integral, which is an electric property. So there's a wave function for the electrons in the atom, and based on their symmetry, the electric field enforces an ordering of the spin that leads to the magnetism, which is why it's such a robust, strong property. So just using a magnet is a fundamentally quantum phenomenon. We're surrounded by transistors. Transistors are fundamentally quantum. So energy goes as the square of velocity. So as I run faster, energy goes as the square of that. What I'm showing here is that parabola. I'm folding it back on itself. But quantum mechanically, what happens is bands open up of forbidden energies. the Fermi energy, which is like the height of a bucket of water if you fill it. In a semiconductor, the Fermi energy is in that gap. Then you can have atoms that either donate electrons or take away electrons, and that's called holes, to dope. And then with that, you make transistors. So if you put a P and an N together, the Fermi energies have to line up the height of the bucket of water, so the bands bend. And so that's why a diode can conduct in one direction but not the other. If you spread out that interface, electrons and holes combine, and that's how an LED makes light. And then if you have a metal insulator semiconductor, when you put a voltage on the metal, you pull the Fermi energy into the band and you induce carriers. And so that charge is the variable resistance of a MOSFET. So anytime you're using a transistor, you're using fundamental quantum phenomena. And now we get to a really interesting one, which is you used your phone probably to navigate here, thanks to handy Google Maps. Google Maps was getting GPS data. GPS data is talking to atomic clocks. And what's going on here, see, Ramsey was a mentor back at Harvard, just a remarkable person. There's a classic atomic clock, there's cesium atoms. I'm showing the energy of the states of the atoms on the left versus the magnetic field. And one state, it goes up, one goes down. So that means if an oven emits cesium atoms and it goes into a non-uniform field, it bends into two streams based on whether they want to go up or down the gradient. Then you go into a microwave cavity, and if you put microwave energy at just the right frequency, you drive the transition between those levels, and you invert which direction they go in the field. So you come back out, you go through another inhomogeneous field, and when you have the frequency right, your detector lights up. And so it lets you find that frequency exquisitely sensitively. And so that's how an atomic clock measures frequency to measure time. Now, when the GPS satellites were launched, they tell you what time it is and where they were. They were post-Newtonian corrections. And it turns out, we've known from Einstein that when you go faster, time slows down. But even more bizarrely, when gravity changes, time slows down. And your GPS receiver on your phone telling you where you are only works because it's using special and general relativity to correct for time dilation and gravitational redshift on the atomic clocks telling you time. So, to use all of this, a few years ago with the US standards body, and shortly you'll hear from the Czech standards body, I ran a meeting on open metrology, on open source scientific instruments. And so one of them is Raman spectroscopy is where you send in a photon and you look at the energy change, and that probes the molecular structure. And it's probably the tool of choice to learn about what molecules are around you. And so this is an open Raman spectrometer, similar, not that far off from a laser cutter, but now probing molecular information. The Open Raman project on the right is one in my lab making an open design for a confocal Raman microscope, so you can image as well as measure spectra. This is a really fun one. I love Antoine Hughes' group. He's done all these inventive things. This version is making an atomic force microscope, which is like a record player, but it lets you measure individual atoms with the needle of the record player. Here it's showing carbon nanotubes, and it's made just with a few buzzer discs. It's actually a surprisingly easy thing. And so these sort of experiments let you access